Now let's solve that same differential equation using Sage. So I've got it started here. I'll go back and forth over here to the whole thing, but I'll add things a little bit at a time. So here I've simply defined t and s. T is our independent variable when we are talking about x of t, and s is our independent variable when we're in the Laplace transform space, and we'll need both of those. And so remember, we had initial conditions, x of 0 was 1, so I have that, and x prime of 0 was 0, so I have that, and a nice comment there pointing that out. And then here we define x as a function of t. That's all that's doing, and making it symbolic. And then here I have a differential equation, and remember it was x double prime, so here's x, take its derivative twice, plus 4 times the first derivative minus 21 times x, and then equals, notice the double equals for an equation. This single equals is assignment. This is for an equation. And then we had 2e to the 4t, and so I can write that way. You know, remember in Sage you have to explicitly do your multiplication with the asterisk. Now, once I have that differential equation, I could have done a show to make sure I got that okay, but I'm not going to do that here. Now here I do the Laplace transform of the whole differential equation, so I just called that LDE, and so there's DE, and to take the Laplace transform I do dot Laplace, and then the variable of x first, and then the variable I want to use for the Laplace transform, s. You could use any variables. Well, here you need t, but if you'd use something else, that would be fine. Just change it here. If you didn't like s, use something else. And so I'll evaluate this to see my Laplace transform, and so you can compare that to our earlier video, and you see it's got the derivative there, 4 there, and all that. Okay, so and notice there's the Laplace transform of e to the 4t, 2e to the 4t there. Okay, so we got that right. And now though, what I want to do is substitute in my initial conditions, and that actually was pretty straightforward. If you look up subs, S-U-B-S, that was pretty straightforward to do that. I just did a substitution of x of 0, just written just like that, x of 0, for the initial condition of x, and did a 1. But working with this one, that was a little tougher. I figured that out, and so let's add in those couple of lines we need there. So I'll go here, grab those 2 lines, and the show from that, and we'll talk about what they're doing. So here, what I did was I defined or assigned to D1 the first derivative of x, okay, and then I said of 0, evaluated at 0, but I did it all symbolically. And so if you do that, you get something that looks exactly like that. And so I found that I had, in order to substitute for that particular expression right there, I had to do it this way. I had to define that derivative, so I did. Then here, what I do is I take this answer that we got down here, and I say dot subs, so I want to do a substitution, and I want to, for x of 0, so for that I want to put in my x0. Now I could have just put in 1, but I think it's a little cleaner to write everything out and what it is, and then use those substitutions. And then for d1, that derivative, that whole expression, I'm substituting my x prime of 0 right here, which was 0. And then I show it, and so let's evaluate that. And we come down and notice I had minus x s of 0, but now it's just minus s because it was times 1. And as we look this way, there's a minus 4 times 1, and then that part was 0, so it just disappeared. So there I have that Laplace transform. Now what I'd like to do is solve that equation. And you could sort of rewrite all this and set up new sage things that solve equations and so forth, but we're a lot less likely to make an error if we never write stuff down ourselves. And so let's do that same sort of thing again that I just did, in that what I want to do is define that Laplace transform of x, because you see I need to solve for that whole thing. That's one item. I want to solve for that whole thing. And so to do that, again, what I did, once I figured out that nifty little trick, I defined the Laplace transform of x this way, x dot Laplace transform, and use that same t and s. So there I'm saying I define that Laplace transform. Here then, now I'm going to get rid of this for a moment. Okay, and so this is what I did first was, so I defined that Laplace transform, and then I said solve that expression up there for that Laplace transform. So I'm saying solve this equation for the L of xt and ts. Okay, so I evaluate, I show that x. And you see I get this answer, but one thing I noticed was, oh, that's inside square brackets. Well, I want to be able to get to just this right-hand side over here. So first I have to get it out of the square brackets. So the way I get it out of the square brackets, now I'll get rid of this part, is I put square brackets and then I say, well, what row was it in the square brackets? Well, there is only one row, and our first row starts at row 0. And so I said, okay, take the first row out of that thing. Now if I evaluate and look at that, notice it got rid of the square brackets. Now I want the right hand side over here. I want this right hand side. And well, Sage has a nice way of doing that. You just tell it, okay, dot right hand side. Now in this case you need to open parentheses because it's a function you're doing here. And so now when I evaluate, I will see that I just have that right hand side. So that's great. So that's what I need to work with. And so finally, there's my Laplace transform of the answer. And I go here and I get my last two lines where I actually come up with that solution. And so you see here I'm saying x solution. Now I would have just used a lowercase x, but we've got that defined here as just that general function of t, so I didn't want to mess that up. So I've got x solution, and I take that my Laplace transform, this thing down here, I take that Laplace transform and just say, well, I want its inverse. And notice when I do that, the s and t are reversed of when I took the Laplace transform. So I do that, and then I show that solution, evaluate, and there it is. I have my 2 over 11, I remember that, e to the 4t, 1/2 e to the 3t, and my 7 over 22 e to the negative 7t. So I end up getting that same solution, but using Sage to do all my calculation tasks. So I had to still know the steps. You know, I still needed to know those steps of define my differential equation, take the Laplace transform, substitute in my initial conditions, solve for the Laplace transform, and then take that inverse Laplace transform. So I still needed to know all those steps, but I got Sage to do the actual calculations for me and the substitutions, so that I was a whole lot less likely to make a calculation error. I mean, I still could in some way, but there are my steps for using that, and I will toss this script up on Blackboard. So there is Sage for our second example, and it's pretty nice.